So, good morning. Thank you for being here. My thesis is oriented towards the development and characterization of a microwave heterogeneous plasma thruster. Okay, so as it was mentioned before by other presentations, usually in the current satellite market, the majority of the satellites use ion thruster and Hall thruster for propelling the spacecraft, but this kind of thrusters use electrodes, and these can be easily eroded by the plasma with time. So this is why the community is going towards electrodeless plasma thrusters like Helicon, VASIM, or ECRT, which is the topic of my thesis, and is a similar concept to what was shown by Celian. So the electron cyclotron resonance thruster was first researched in the 60s. But then it was soon abandoned in favor of the new technologies like ion thruster and Hall thrusters that were seen to be more efficient. But some recent advances on a coaxial version of the ECR thruster brought by Onera made this topic more interesting for the scientific community and made it desirable to investigate more on that. So, in fact, developing of a waveguide ECR thruster allows to have the possibility to study a variety of different topics like magnetic nozzle, plasma wave interaction, and also it offers a good platform for a validation of simulation code. So, as you can see, there are two different types of up to now ECR thruster. There is a coaxial version by Onera and waveguide version that was investigated in the past, and it's the topic of my thesis. And the difference between these two is the presence of an electrode in the middle of the channel of the coaxial version, which is as well subject to erosion. Thus, the coaxial version is not really completely an electrodeless thruster. This is why also we are interested in studying better the waveguide ECR thruster. My thesis was basically focused on this topic, and the development of the thesis was divided into three main parts: the design of the thruster, the modeling of the thruster using our simulation platform, which is called IFAN for discharge physics of internal discharge physics of the thrusters, and the experimental characterization of the device using different plasma diagnostics customly applied to this thruster. Okay, so here I present briefly the thruster design. The working principle was already explained by Celian in the previous presentation, but basically you need two components for these thrusters to work. You need a microwave source, which will be absorbed. The microwaves will be absorbed efficiently by the electron cyclotron resonance in the electron cyclotron resonance region. They will be absorbed by the electrons in the region in which the magnetic field is such that the electron gyration frequency is the same as the applied electromagnetic wave frequency, which in this case is in the microwave range. Then the acceleration, the electrons absorb efficiently the electromagnetic wave and they ionize the plasma. And then in order to produce thrust, we need to accelerate the ions, and this is made by a magnetic nozzle. In this design, so the microwaves are propagating through the waveguides coming from the generator, and this is the plasma chamber. Inside the plasma chamber, we have the ECR resonance, the electron cyclotron resonance, and the magnetic nozzle is developed by this magnetic field generator, which is a composition of a permanent magnet and a coil. The permanent magnet creates the base field of the magnetic nozzle, and the coil can be used to tune this magnetic field to alter the shape of the magnetic nozzle and to have a more focused beam. The design was supported by multiple types of simulations like thermal analysis, microwave propagations, and magnetic field simulations. The working range of this thruster is around 50 to 350 watts. This is what we tested, and it can work with mass flow rates higher than 1 SCM in general. Okay, so I'm close to the end of my thesis. Thus, a lot of the work has already been done. So in the first year, I was focusing, because of the pandemic, on the simulation of the discharge chamber using the IFAN code. And this work was presented in a conference. We expect to contribute more on this work by implementing by testing one more time the thruster with an improved version of the code. Sorry. It's because I don't see well. With an improved version of the code, which couples better the wave plasma module with the transport. Then in 2021, we achieved the first thruster ignition. And we already published this result in a journal paper. And last year we performed the first thrust measurements, so we were able to assess the performance metrics of the current prototype. Always in this last year, I was focused on LIF measurements and other diagnostic techniques. In particular, the LIF technique was used on my thruster in collaboration with the SNSC car. Studied the magnetic nozzle, and I also applied the LIF technique during my research stay at the JAXA facilities. Now I'm currently working on an experimental campaign involving Faraday cups, but since there is not so much time to discuss about this, I will not present it in this presentation. Okay, so because of this, I first introduce a little bit more about what is actually the LIF technique and how it works. The LIF technique offers a lot of advantages in the sense that it's able to provide information on the ion velocity distribution function, and is able to do this non-intrusively and with the high spatial resolution. This is something that no other probe can provide. Okay, so everybody knows how more or less ion transitions and atom transition work. So when an atom is excited, after some time in the order of nanoseconds, they will come back to a lower energy state, emitting some photons. So, this transition to the higher energy state can be excited by providing the photon necessary for the transition. And thus, then the atom will fall back to the base level or to another metastable level. In this way, if we provide these photons, for example, with a laser light, we are able to collect the emitted light, which in this case will be a fluorescence light. And we can correlate the light emitted for a specific wavelength with the velocity of the ions. This is possible thanks to the Doppler effect. In fact, in a moving reference frame, we have that the atoms or the ions will be absorbing not the reference wavelength when they are at rest, but wavelength that is shifted because of their speed. And then by collecting the light for that specific wavelength, we are able to obtain the ion velocity distribution function. I will explain this a little bit in the more details here. Okay, so here what we see is the plasma volume, the state that we want to analyze, and there are ions with different velocities in the middle of it, and we shine a laser with a varying wavelength in the plasma, and the whole region which will be of the plasma, which will be subject to this laser, will start to fluoresce. But since we want a spatial resolution, we want to investigate just one specific region, and so we focus our detection optics inside, in just one single point. And this will provide a resolution up to some millimeters, like 2 or 5 millimeters range. So what we do is to scan the laser at different wavelengths, and we collect the emitted fluorescence light for each of these wavelengths. What we will observe directly from the output of our detection optics would be something like this. This is a convolution of multiple factors, multiple broadening mechanisms. First of all, we have, of course, the hyperfine structure of the atom, which is basically in the range that we want to study of frequency of the wavelength. There could be multiple transitions, multiple of these transitions that could cause fluorescence. So they will be seen as a distortion of the hypothetical velocity distribution function, but also there are other shifts like isotopic shifts or caused by magnetic fields or electric fields. In particular, the ones due to the magnetic fields are important in our case because there are very strong magnetic fields in this kind of thrusters, and they will affect the measurements as we see now. Okay, so as I was mentioning before, the LF technique was used on the device that we have developed at G3SM, but the work was performed in collaboration with Senresi Car, which was providing the LF expertise and instrumentations. The objective of this was to study better the magnetic nozzle physics, but of course to study as well the performance of the thruster and possibly evidence some some loss mechanism. Sorry. Okay, so here we can show some of the results. Well, the setup is very simple. We have the detection optics here, and the laser is shine through here towards the axis of the thruster, like is displayed in the scheme. Okay, so first of all, what we can see here is the different line shapes for different axial positions, so for different position along the axis here. And we see that when we are inside the thruster, the line shape assumes to peak, and this is what is due to the Zeeman effect. The Zeeman effect splits the wavelengths that the ions or the atoms are absorbing, and then we see it as this. So the hyperfine structure of the atoms is different from the base one as a resulting of the interaction with the magnetic field, and this is related to quantum effects caused by the presence of the magnetic field. Going towards the axis, going towards downstream the plume, the magnetic field decreases, as we can see, and the profile assumes better the shape of a Gaussian, which is what we would expect from a ion velocity distribution function, but also the noise increases because of the lower density of the plasma, and so the signal-to-noise ratio results to be lower. Here we can see some results about the actual velocity that we obtained, and you can see that for different magnetic nozzle current, this is the coil current, so it's basically when it increases, the divergence of the beam decreases. We can see that for the different designs, so as I was saying, when the magnetic field increases, the divergence is decreased respect to this case, the base case. Basically, the final velocity happens to be the same for all of the three cases, but what we see is that the acceleration is different in the close region to the exit plane. Also, we notice that we achieve negative velocities inside the thruster. This might be one of the losses mechanisms, so we are losing some ions towards the backplate of the thruster. Also, we see here the behavior of the velocity, mean velocity, when the mass flow rate is changed, and this behavior basically is that when the mass flow rate increases, the final ion speed is also decreased, and this is simply due to the fact that the temperature of the electrons is decreasing, and so also the potential drop available. And when we increase the power, of course, we expect to see, for the same reason, a higher velocity in the beam. This was performed at a constant, in a constant position at varying the power levels. Okay, so I applied this technique as well during my research stay at JAXA on the Hayabusa 2 thruster. In particular, in this case, it is not so easy to explain the reasons why we were performing these measurements, but in principle, basically during the mission, it was observed that the cathode lifetime was differing from the one obtained during the experimental campaigns, and this was due to erosions happening is thought to be due to the erosions happening in the surrounding of the thruster. So for this reason, we wanted to check if this erosion might happen with the velocity that we measure in the actual experiment, and also provide an experimental proof that there is actually charge exchange ions in the surrounding of the cathode. This allowed me to familiarize better with the LIF technique, and also to finalize the experimental setup both inside the vacuum and inside the air segment. Okay, so here we can see the setup that I used. Okay, sorry. Okay, so I guess I will skip these slides and show some results about this campaign. So in this campaign, we were measuring in the proximity to the cathode, and we can see that the noise level is quite high, and this is due to the very low density that was available in this region. And also we see that the velocities are very close to zero. So this proves that these are charge exchange ions that are produced around this region. Also, the velocity that we measure differs a lot in the z direction, the axis of the thruster, and also in the radial direction. In particular, in the z direction, we've seen this very low velocity, but in the radial direction, we have seen velocities up to 1,000 meter per second. This is not enough for causing sputtering, but we have to include also the effect of the sheaf that will accelerate the ions towards the surfaces, but as well the fact that the ion has a distribution, the ion velocity distribution function has a tail, and this tail could explain some part of the erosion. Okay, so concerning my future works, I will finalize the journal paper dedicated to the thrust measurements that I performed last year, and finalize as well the measurements with the Faraday cups that I'm performing right now. And as I was saying before, I also will focus more on the simulation of the plasma discharge chamber, and finally finalizing the thesis with this manuscript. So this is my scientific contribution. I worked on 2 journal papers, one as a second author and one as a first author. These are the conferences to which I participated, and the research stay at Doctoral. Thank you for your attention.